Hello, this is Professor Dan Kernler of Elgin Community College. This is another video in my statistics series. In this one, we introduce the concept of hypothesis testing. Okay, let's get to it. All right, you know the drill by now. We're going to introduce this idea by way of an example. I have some US Census data. Specifically, I have education data. This is for population ages 25 and older, and about 42.3% have at least an associate's degree. And we have a database we can compare. We have the children of immigrants, and I have this table for the children of immigrants. If we look at those who have an associate's degree or more, it's actually 56.9%. Now, one caveat here, I'd encourage you to investigate the source for this data. I'll link it in the description. This is a selection of children of immigrants from a couple of specific communities, and they found them in schools and then followed up with them later. So it is quite possible that because of the way they followed up with them, they may not have a representative sample of all children of immigrants. It may be because of the way they selected them, possibly why this is clearly higher, at least on the surface. But what we want to do is we want to investigate this difference and see if this difference actually has some statistical meaning. The way we're going to do that is we're going to analyze the sample proportion. So you recall, if we have n times p times 1 minus p, and that's at least 10, then our sample proportions should be approximately normally distributed. So let's look at the numbers that we have. The total in our sample is 3,296. That's our n. We'll plug that in. And then the P, that's the population proportion, that's going to be the 42.3%. That's the proportion of all American adults who have a associate's degree or higher, 42.3%. So we'll plug that in and do a check, and it is at least 10. So that means we should fit this approximately normal distribution. The mean of all the sample proportions should be the same as the population proportion, and the standard deviation is square root of p times 1 minus p all over n. So for our particular numbers, we plug those in. We have a mean of 42.3%, a standard deviation of this 0.00875. If we go out those standard deviations, here is the distribution of all the sample proportions. What this is, to be clear here, is if we take a random sample of 3,296 individuals, the proportion who have an associate's degree or higher should follow this distribution shape. Okay, well, where is ours? Ours is 56.9%, which on the distribution, way over here. So clearly we have something unusual, but what if it had only been like 44.5% or 44.4% or 43.7%? Would those have been unusual enough for us to say that the proportion appears to be higher? Well, we need some stronger criteria in order to make a decision. What we're going to do is we're going to develop a new process called hypothesis testing. So let's dive into that process and how the process works. The first thing we need is some vocabulary. We're going to introduce something called the null hypothesis. The notation here is H with a subscript of 0. And this is what we assume to be true until proven otherwise. That's the null hypothesis. The alternative hypothesis, the H sub 1 or H sub A, depending on your textbook or your preference, that's the claim that we're testing. That's the thing we're wondering if it is true. That's the difference. For our specific example here, the null hypothesis is that the proportion is the same as it is from the US Census here, 42.3%. Our alternative claim, now we're going to be a little bit careful here. We're claiming that it's greater than. Now, for other tests here, it might be less than, it might be not equal to. We're going to do greater than. I want to be really careful though. We really kind of did this backwards. We looked at our data and said, oh, hey, look, it's 56.9%. I wonder if ours is statistically greater. We really should have these questions before we look at the data. That's what statisticians do, is they have some question, then they look at the data and see if how the data answers their question. You shouldn't be digging into data and seeing, oh, here's something different. Let's see if there's a statistical difference. So just as a caveat there, that's how we should set up these alternative hypotheses. Okay, so Let's talk about some things that can go wrong. Suppose we make a conclusion. We say, hey, children of immigrants are more likely to earn their associate's degree by age 24. What if that's wrong? We have a label for that. We call that a type 1 error. What if we had said, hey, nope, it looks like they're similar, and they're actually not? Well, then in that case, would we call that a type 2 error? One thing I like to do to help students understand these is make a little grid. So let's say on the vertical here, we have our decision, the actual decision we would make. And then on the top, we'll have what is actually true. So we might decide that the proportion is 42.3%, and the reality either is or it's greater than that. So in the top left box here, we decide, yep, it seems like the proportion is 42.3%. If that's actually true, hey, then we're correct. We did it right. If we move down, we decided that the proportion was greater than 42.3%, but really it wasn't. So that would be the type 1 error. We would reject the null hypothesis. We said it wasn't 42.3%, but really it was. And so we made a mistake. Moving over, here we decided, hey, it's greater than 42.3%. It actually was greater than 42.3%. That would be correct. And then the top left one here, we didn't reject the null hypothesis. We said, hey, it looks like it could be 42.3%, but actually it was greater than. That's the type 2 error, when you don't reject the null hypothesis, but you should. If we generalize this, again, the type 1 error is you say the alternative is true. You're going to reject the null hypothesis, but really the null hypothesis is true. You made a mistake. That's a type 1 error. And then type 2 is you didn't reject the null hypothesis. You said, well, maybe the null hypothesis could be true. I'm not going to reject it, but you should. The alternative hypothesis was actually true. That's a type 2 error. More notation for you. The probability of a type 1 error, we use the letter alpha for that. And you might recognize that from our confidence intervals in our Z sub alpha. There is a reason for that. That's going to be a trend here. That is also called the level of significance of the test. For the type 2 error, probability of a type 2 error is beta. That's the power of the test. We're not going to talk a lot about that one in this class. That requires a little more sophistication, and that's something that if you want to learn more about, you can investigate that on your own. I didn't do a lot of research and start trying to manipulate the power by looking at the test into some of my later statistics classes. So how do we make a decision in our hypothesis test? Well, we have our distribution shape. What we're going to do, there's two different methods. One method is we're going to put a value here over on the right that would have alpha area to its right. And we're going to call that the critical value. That region over there on the right is the critical region. And we're going to say, hey, if we observe anything over there, further over there, then we're going to conclude that the null hypothesis must have been incorrect. And we think the alternative is true. The second method is we're going to compute our sample statistic. We've got it. Let's say it happens over here on the right. We're going to find the probability of being to the right. That's called the p-value. And if our p-value is less than alpha, the level of significance, we're going to reject the null hypothesis. This is not an easy concept to wrap your head around. So I tried to develop, how could I help students visualize this? So let me take another stab at this and see if this helps. I've got all these blocks. Say these represent all the different things that could happen with our sample proportions. Most of the time, right, it'll be in the middle. Sometimes it'll be in the tails. For the critical value method, what we're going to do is we're going to put some values over here on the right. And we're going to say, you know what? If we have something that happens over there, we're just going to be okay if we're wrong. And we're going to say, you know what? If it happens over there, the distribution is probably over to the right somewhere. We might be wrong, but we're just going to say, hey, that's an acceptable error there. We think the probability or the distribution shape is probably over to the right somewhere. For the p-value method, it's kind of similar. We're going to say, okay, again, these probabilities or these things that happen over here on the right, they're acceptable error rates. If we have something that's less likely, so we have these less blocks, hey, that's less likely than our acceptable mistake rate. Hey, then we're going to reject the null hypothesis. And again, we think the distribution shape is over here to the right somehow. I don't know if that helped, but that's the idea behind those two methods. We're looking for extreme observations. And if we get something that happens way out on the edge, that means our null hypothesis is probably not true. And we're going to reject it and support our alternative. I should say here, by the way, I'm doing all things over on the right. Hypothesis tests can be on the right, they can be on the left, they can be a two-tailed test where it could go either way. All right, now to the actual testing process. We're going to have 6 steps, and we're going to do these same 6 steps for every hypothesis test. In fact, pretty much the rest of the videos this semester, I think that's all of them, actually. Yeah, I think every video for the rest of the semester, we're going to use these same 6 steps. In fact, when I was designing the animations for these, I used the same sequence of animations for every single one. And you need to do this for my students in your exams as well. You need to use these same 6 steps. First step, define your null and alternative hypothesis. Second step, choose your level of significance. When in doubt, you can choose the 0.05, but depending on the consequences, if you make a type 1 error and that's a really bad mistake, maybe you're going to give someone a drug that has a chance of killing them, maybe you put 0.01 or 0.001 as your level of significance. Depends on the consequences of that type 1 error. Then you compute your test statistic. We're going to have a variety of test statistics. Then you compute the p-value or critical value depending on which method you are using. I like to use the p-value method, that's more common, but there are some dangers with it, and I'll talk about those a little bit later. Then you make your decision. Do you reject or not reject the null hypothesis? And then you summarize it with a nice sentence with a conclusion. For our example, our null hypothesis was that the proportion of people who have an associate's degree or more is the same as the population, 0.423. Our alternative is that we think it's greater than. The alpha, the level of significance, let's just use the default, the kind of typical, like, is it an unusual observation, this 0.05? It's a pretty common one to use for your threshold. The test statistic, I'm not going to go into how this is computed. That'll be in the next video. But that's actually a z equals 16.88. Now, if you know about the z, the normal, wow, that is a really, really, really big z, okay? So when you compute the p-value or the critical value, well, for the p-value, that's the probability of being way over here. It's basically impossible. Now, we don't say p is 0 because it isn't technically 0, but it's like 0.0000, whatever. It's really, really, really small. So the p-value there, we would just say it's less than 1/10,000th. If you get something less than 1/10,000th, you just literally write p-value less than 1/10,000th. The z, the critical value here, happens to be 1.645. That might look familiar. Again, we're not going to talk about that in this video into the specifics. This was more of a conceptual video. Now, we observed something very unusual. So if you think about it, then our decision is going to be to reject the null hypothesis. So our decision here, the odds of getting something out here randomly, basically impossible. So we're going to reject the null hypothesis. That means we do not think the proportion is 0.423. So for our conclusion then is we're going to say, okay, we are going to reject the null. We think the alternative is true. So the wording here is there is enough evidence at the 0.05 level of significance to support the claim that the proportion of the children of immigrants who have earned a degree by age 24 is higher than the general population. That wording there, you will see this kind of wording over and over. It's just a cutoff yes or no. Is there enough evidence to support your claim or not? In this case, we do. We have a very, very, very unusual observation. It's probably not that same proportion. So in this case, we would conclude there is enough evidence to support our alternative claim. Now, there are a few really, really big, important issues with hypothesis testing that we need to discuss. The first is the issue of sample size. So we have this distribution shape, right? And say we observe something, we get a sample proportion here. That might not seem unusual. But if you have a larger sample size, your standard deviation will get smaller. And then suddenly, if you happen to get that same sample proportion, now it looks unusual. So sample size has a huge effect on the p-value. So you have to be careful and say, well, look, this test wasn't significant. This test was, but this is a huge sample size. Sometimes differences that are really minor end up looking significant just because you have 10,000 in your sample. You really have to be careful, and we'll talk about some alternatives that you can use to get more meaning from it. Just because it's a significant test doesn't mean it actually has some meaning. The next issue here is there's some like publication issues with what types of studies get published and what p-values do they have. For example, if you look down here, you can see look at this little weird jump. It looks like p-values right before 0.05, there's a little jump. And certainly the smaller your p-value, the more likely you are to publish. This is a problem. This means that people who get statistically significant results are more likely to publish, whereas if you looked for a difference and you did a bunch of research and it wasn't statistically different, you just didn't publish. But then we don't know that there isn't a statistical difference. If you zoom in and get like finer detail around 0.05, you can see, if we zoom in and get to the nearest, what would that be, an eighth of a thousand? So look at that spike right below 0.05. So 0.0495 gets published, but 0.05 doesn't. So there are some issues with this threshold of 0.05 and what gets published and what doesn't. It is definitely a problem and something we want to think about as we study this. And I don't know if this is going to be helpful, but to illustrate this, I've got a few memes that really point this out. So when your p-value is just below 0.05, yes, right? P-value, when you do a research study and you get significance, it's like, oh, it's the best. Oh no, your p-value is 0.05, so we failed to reject you. This one, like, oh, poor guy, your p-value is 0.056. So all of these are pointing out to like, there's this like huge thing about 0.05 is like this big deal. So we have this issue of certain p-values getting published and others not. That's like a publication bias. If you have a statistically significant result, it's more likely to be published. But there's also an issue of p-hacking. This is like repeating an experiment over and over and over, and then just publishing the ones that ended up being significant. Remember, if this is your distribution of your sample proportion, your population proportion should be in the middle. Some of your sample proportions will be to the left, some will be to the right, some will be over here. But if you do a bunch of these, eventually you'll get something that's way over on the edge and looks significant. So my favorite example of this is this XKCD comic. So you've got here, they're looking at jelly beans and they investigate and they found no link between jelly beans and acne, p greater than 0.05. So what if it's different colors? And then all the different colors and whoa, hey, look, green, there's statistical significance. And then so it gets published, green jelly beans are linked to acne. This is p-hacking, where they did 20 different experiments and they just got one of the 20 that happened to randomly be extreme. This is a real issue. And they actually test this where they'll try to do these replication studies, where they'll look at studies that have been done and they'll try to replicate them. And often when they try to replicate them, they can't get the same results because that person might have done 5 different experiments and then they only published the one that ended up being significant. Now, this is not to say that we should never do hypothesis testing and p-values are pointless. We just have to be really careful about it and really kind of thoughtful about what does it mean? What does our decision mean? Why should we only publish not significant results? Maybe we should publish not significant ones too. Those are valuable. There's a good article here if you're interested in more from FiveThirtyEight about, it's not that science is just broken, it's just really hard and it's hard to interpret it. It's hard to explain it clearly to people who don't have this background. So I do want to soften that. I don't want to say that hypothesis testing is pointless. We're going to spend the rest of the semester doing it, but it is hard and we need to make sure we're really thinking carefully about what we're doing. All right, that is it for this video. This is another heavy one, big concept here of hypothesis testing. It's really important that you have a good, solid foundational understanding of this though, because like I said, we're gonna do this for the next set of all the rest of the videos. So it's really important that you understand the main concepts from this one. I hope you enjoyed watching this. If you're interested in seeing more, you can subscribe, hit the bell to get notified. As always, thank you to the Elgin Community College Board of Trustees who approved my sabbatical for the spring 2021 semester. And that's what gave me the time to film, record, edit, produce all of these videos for you to watch. Thank you so much for watching, and I will see you in the next one.